Hello again. Let's continue with system services. Another aspect of a modern system is its collection of system services. Please recall the logical computer hierarchy. At the lowest level, we have hardware. Next is the operating system, then the system services, and finally the application programs. System services, also known as system utilities, provide a convenient environment for program development and execution. They can be divided into these categories: file manipulation, status information, programming language support, program loading and execution, communications, background services, and application programs. Also, we have to say that most users' view of the operating system is defined by system programs, not the actual system calls. Some of the system services are simply user interfaces to system calls. Others could be more complex. So here are the system services categories. File management. These programs create, delete, copy, rename, print, list, and generally access and manipulate files and directories. Status information. Some programs simply ask the system for the date, time, amount of available memory or disk space, number of users, or similar status information. Others are more complex, providing detailed performance, logging, and debugging information. Typically, these programs format and print the output to the terminal or other output devices. Some systems also support a registry, which is used to store and retrieve configuration information. So these are the part of status information. And file modification. Several text editors may be available to create and modify the content of files stored on disk or other storage devices. There may also be special commands to search contents of files or perform transformations of the text. Programming and the last one is programming language. Sorry, not the last one. The next one is the programming language support. Compilers, assemblers, debuggers, and interpreters for common programming languages such as C, C++, Java, and Python are often provided with the operating system or available as a separate download. The next one is program loading and execution. Once a program is assembled or compiled, it must be loaded into memory to be executed, as you know. The system may provide absolute loaders, relocatable loaders, linkage editors, and overlay loaders. And debugging systems for either high-level languages or machine language are needed as well. Communications. These programs provide the mechanism for creating virtual connections among processes, users, and computer systems. They allow users to send messages to one another's screen, to browse web pages, to send email messages, to log in remotely, or to transfer files from one machine to another. So for that purposes, we need to create communications between processes. Background services. All general purpose systems have methods for launching sorting system programming process at boot time. Some of these processes terminate after completing their tasks, while others continue to run until the system is terminated. Constantly running system program processes are known as services, subsystems, or daemons. Along with system programs, most operating systems are supplied with programs that are useful in solving common problems or performing common operations. Such application programs include web browsers, word processors, text formatters, etc. The view of the operating system uh, seen by most users is defined by the application and system programs rather than by the actual system calls. So if you are a user, the communication between operating system and you is basically applications and system programs. So we have some details here. Actually, you can remember the basics of linkers and loaders from our programming courses. Usually, a program resides on disk as binary executable file. To run on a CPU, the program must be brought into the memory and placed in the context of process. Source files are compiled into object files that are designed to be loaded into any physical memory location, a format known as an relocatable object file. Next, the linker combines these relocatable object files into a single binary executable file. During the linking phase, other object files or libraries may be included as well. A loader is used to load the binary executable file into memory. An activity associated with linking and loading is relocation, which assigns final addresses to the program parts and adjusts code and data in the program to match those addresses. The process we described here assumes that all libraries are linked into the executable file and loaded into memory. In reality, most systems allow a program to dynamically link libraries as the program is loaded. Windows, for instance, supports dynamically linked libraries, and generally they're called as DLLs. The benefit of this approach is that it avoids linking and loading libraries that may end up not being used into an executable file. Instead, the library is conditionally linked and is loaded if it's required during the program runtime. Object files and executable files typically have standard formats that include the compiled machine code and a symbol table containing metadata about functions and variables that are referenced in the program. Here in this figure, we can see that to run the loader, all that's necessary is to enter the name of the executable file on the command line or just clicking it. When a program name is entered on the command line on Unix system, for example, let's say we have /mainc, the shell first creates a new process to run the program using the fork system call. The shell then invokes the loader with the exact system call, passing exact the name of executable file, and the loader then loads the specified program into memory using the address space of the newly created process. So why applications are operating system specific? Fundamentally, applications compiled on one operating system are not executable on the other operating system. If you compile your program on Windows, you cannot directly execute that compiled code on Linux or macOS. If they were, the world would be a better place, and our choices of what operating system to use would depend on utility and features rather than which applications were available. But it's not. Based on our earlier discussion, we can now see part of the portable. Each operating system provides a unique set of system calls. System calls are part of the set of services provided by operating systems for use by applications. Even if system calls were somehow uniform, other barriers would make it difficult to use to execute application programs on different operating systems. So this is the short answer. We use different system calls on different operating systems. For that reason, we cannot directly execute all programs on all different operating systems. So we can continue with design and implementation of operating systems. In this section, we are going to discuss problems we face in designing and implementing an operating system. There are, of course, no complete solutions to such problems, but there are approaches that have proved some success. The first problem is actually in design a system is to define goals and specifications. At the highest level, the design of the system will be affected by the choices of hardware and the type of the system. It could be a traditional desktop, laptop, mobile, or distributed or real-time system. So based on the difference on that systems, it is going to affect your design. Beyond this highest design level, the requirements may be much harder to specify. The requirements can, however, be divided into two basic groups: user goals and system goals. Users want certain obvious properties in a system. The system should be convenient to use, easy to learn, and to use, reliable, safe, and fast. The system goals, actually, the system should be easy to design, implement, and maintain, and it should be flexible, reliable, error-free, and efficient. So specifying and designing an operating system is a highly creative task. Although we can directly say that no textbook or no course like this can tell you how to do it. So in this course, we cannot cover every subject. We cannot cover every aspect. So no textbook or no course cannot tell you how to design and implement an operating system directly. But general principles have been developed in the field of software engineering, and we can describe them, we can cover them. And we turn now to a discussion of some of these principles. One important principle is the separation of policy from mechanism. Mechanism determine how to do something, and policies determine what will be done. So policy asks what needs to be done, and mechanism asks how to do something. For example, the timer construct is a mechanism for ensuring CPU protection, but deciding how long the timer is to be set for a particular user is a policy decision. The separation of policy and mechanism is important for creating a flexible mechanism for flexibility. Policies are likely to change across places or over time. In the worst case, each change in policy would require a change in the underlying mechanism. For that reason, we have to specify the difference between policy and mechanism. A general mechanism flexible enough to work across a range of policies is preferable. Once an operating system is designed, it must be implemented. Because operating systems are collections of many programs written by many people over a long period of time, it's difficult to make general statements about how they are implemented. Early operating systems were written in assembly language. Now, most are written in higher level languages such as C or C++, with small amounts of the system written in the assembly language, but still in some cases we need to use assembly language on exactly low levels of operating systems. In fact, more than one higher level language is often used. The lowest levels of the kernel might be written in assembly language and C. Higher level routines might be written in C, C++. And system libraries might be written in C++ or even a higher level language. The advantages of using a higher level language, or at least a system implementation language, for implementing operating systems are the same as those gained when the language is used for application programs, which is the code can be written faster, is more compact, and is easier to understand and debug. The only possible disadvantage of implementing an operating system in higher level languages are reduced speed and increased storage requirements. This, however, is not a major issue in today's systems. A system as large and complex as a modern operating system must be engineered carefully if it's to function properly and be modified easily. A common approach is to partition the task into small concepts or modules rather than have one single system. Each of these modules should be well-defined portion of the system with carefully defined interfaces and functions. We briefly discussed the common concepts of operating systems. In this section, we are going to discuss how these components are interconnected and melted into kernel. So we have simple structures, a bit more complex structures, layered abstractions, and more complex structures can be defined as microkernels or microkernels. The simplest structure for organizing an operating system is no structure at all. That is, place all the functionality of the kernel into a single static binary file that runs in a single address space. This approach, known as a monolithic structure, is a common technique for designing operating systems. An example of such limited structuring is the original Unix operating system, which consists of two separable parts, the kernel and the system programs. The kernel is further separated into a series of interfaces and device drivers, which have been added and expanded over the years as Unix has evolved. We can view the traditional Unix operating system as being layered to some extent, as shown in this figure. Everything below the system call interface and above the physical hardware can be described as the kernel. The kernel provides the file system, CPU scheduling, memory management, and other operating system functions through system calls. Taken in sum, that is an enormous amount of functionality to be combined into one single address space. The Linux operating system is based on Unix and is structured similarly as shown in this figure. Applications typically use glibc standard library or general C standard library when communicating with the system call interface into the kernel. The Linux kernel is monolithic in that it runs entirely in kernel mode in a single address space. But as we shall know in the next sections, it does have a modular design that allows the kernel to be modified during runtime. So file system, CPU scheduler, memory managers, etc., they can be described as different modules. Okay, they are the part of the kernel, but we have a modularity in this kernel. The monolithic approach is often known as a tightly coupled system because changes to one part of the system can have wide range effects on other different parts. Alternatively, we could design a loosely coupled system. Such a system is divided into separate, smaller components that have specific and limited functionality called as modules. A system can be made modular in many different ways. One method is the layered approach, in which the operating system is broken into a number of layers or levels. The bottom layer, layer 0, is hardware. The highest level, let's say layer N, is the user interface. This layering structure can be seen in this figure. Layered systems have been successfully used in computer networks such as TCP/IP, as you know, and web applications. Nevertheless, relatively few operating systems use a pure layered approach. One reason involves the challenge or appropriately defining the functionality of each layer. So this layered approach is just an idea. Let's continue with microkernels. We have already seen that the original Unix system had a monolithic structure. As Unix expanded, the kernel became large and difficult to manage. In the mid-1980s, some researchers at Carnegie Mellon University developed an operating system and called it as Mac that modularized the kernel using the microkernel approach. This method structures the operating system by removing all non-essential components from the kernel and implementing them as user-level programs that reside in separate address spaces. The result is a smaller kernel. The main function of the microkernel is to provide communication between the client program and the various services that are also running in user space. Communication is provided through message passing. So advantages of the microkernel approach can be numbered as easier to extend a microkernel, easier to port the operating system to new architectures, it will be more reliable, and it will be more secure. But the main disadvantage of this approach is performance overhead of user space to kernel space communication. If you move some parts of kernel to user space, that means you have to create more communications between user space and kernel space. And here we have an example. So on the monolithic kernels, this file system and device drivers are the part of the kernel too. But on the microkernel system structure, we removed that unnecessary parts from the kernel. So interprocess communication, memory management, CPU scheduling, etc. are the part of our kernels, but we moved file system and device driver from kernel to user mode. So assume that an application program wants to open a file. So in that case, it has to create a system call to the operating system. But the file system management is not the part of kernel mode. So to use file system, the operating system on the kernel mode has to create a communication mechanism again with the user mode, because file system are on the user mode too. So file system has to create a message, again has to return or switch to kernel mode to use device drivers, but the device drivers are not the kernel too. So we have to create a new communication line between kernel mode and user mode too. So this is the main disadvantage of the microkernel approach. Performance overhead of user space to kernel space communication. Perhaps the best current methodology for operating system design involves using loadable kernel modules, or let's say LKMs. Here, the kernel has a set of core components and can link in additional services via modules, either at boot time or during runtime. This type of design is common in modern implementations of Unix, such as Linux operating systems, macOS operating systems and Solaris operating systems, as well as Windows. So basically, modern operating systems use loadable kernel modules because they use object-oriented approach. Each core component is separate. Each talks to the others over known interfaces. Each is loadable as needed within the kernel. So they are not the part of kernel when the boot time, but when you need that module, instead of executing it on the user mode, you are going to take that module into your kernel. You are going to load that module to your kernel. So you are going to extend your kernel if you need to use that module. In practice, very few operating systems adopt a single strictly defined structure. Instead, they combine different structures, resulting in hybrid systems that address performance, security, and usability issues. For example, we can describe Linux is monolithic because having the operating system in a single address space provides very efficient performance. However, it's also modular, so that new functionality can be dynamically added to kernel. Windows can be described as largely monolithic as well, again, primarily for performance reasons, but it retains some behavior typical of microkernel systems, including providing support for separate subsystems known as operating system personalities that run as user mode processes. Windows systems also provide support for dynamically loadable kernel modules too. Also, the Apple's macOS operating system and the two most popular mobile operating systems, iOS and Android, are hybrid systems too. So basically, we can say that, okay, our modern operating systems generally use modules, but we can describe them generally monolithic structures because the performance is very important for operating systems. So basically, we can say that, okay, these operating systems use different approaches to create their system. For that manner, we can call that operating systems as hybrid systems. And that's it for today. Any question? Next week, we're going to start to discuss about processes. We are going to describe what is a process and how we can load that processes to memory. And we are going to continue with process management. But before that, we covered operating system concepts and operating system structures before starting to that deeper sections. Any question? Okay then, if you don't have any question, that's it for this week. See you later.